Hello everyone, this is Zhali Duan. Today I'm going to present our paper, Slade, a self-training machine learning framework. This is a joint work from University of Southern California and Amazon. Many thanks to my collaborators. They are Yanliang Lin, Sang Tran, Larry Davis, and CCJ Cole. A recent study shows that existing machine learning methods perform similarly when hyperparameters are properly tuned, despite employing various forms of losses. In this paper, we'll explore another direction by utilizing additional on-label data. Recent papers show that self-supervised approaches and self-training approaches have shown promising results utilizing on-label data. Self-supervised approaches is able to learn generic features which can be transferred to downstream tasks via fine-tuning. This diagram shows an example of self-training framework which improves the fully supervised approaches using a teacher-student paradigm. However, existing methods mainly focus on classification, not retrieval. Here is an overview of our proposed self-training framework for deep machine learning. It mainly consists of three main steps. In step 1, we perform self-supervised pre-training and fine-tuning for the teacher model. In step 2, we use the teacher network obtained in the first step to generate pseudo labels on the on-label data. And in step 3, we perform joint optimization of student network and basis vectors. Now let's break down the details of each individual component. In step 1, we perform self-supervised pre-training and fine-tuning for the teacher model. Specifically, we initialize the teacher model with a self-supervised model weight. And then we perform pre-training of the teacher model using both labeled and unlabeled data without using labeled information. Then we fine-tune the teacher network on the labeled data using ranking laws. Note that the approach is independent of the self-supervised model being chosen. They can be SWAV, BYOL, or MOCL. In step 2, we use the teacher network to generate the pseudo labels for the unlabeled data. We perform k-means clustering to generate cluster ID for each of the individual sample. Note that the pseudo labels generated in this step are often noisy. In step 3, we perform training of the student network. The student network consists of a student backbone and an embedding layer, and our goal here is to learn better embedding representation. We further introduce a feature basis learning component to help deal with the noisy pseudo labels generated in step 2. We use cross-entropy loss on the labeled data, similar to distribution loss on unlabeled data, and we jointly optimize the student and the basis vector in an end-to-end manner using the following objective. Now we take a further look at the feature basis learning component. Conceptually, the feature bases are a set of learnable weight vectors which can be used to measure pairwise similarities. On labeled data, we use cross-entropy loss to directly optimize it. And on unlabeled data, we calculate the pairwise distances and model the pairwise similarity as two global Gaussian distributions. Our goal here is to reduce the overlap between these two distributions by maximizing the distance between two means and reduce the variances of two distributions. For each batch coming in, we calculate the local means and variances and use them to update the global means and variances in a momentum manner. By putting it all together, we get the training and testing pipeline of our framework. During training, we use the teacher to generate pseudo labels for the student, and we train the student with the basis vectors using both labeled and unlabeled data. When the student is trained, it is used to replace the teacher for the next iteration. We perform this iteration several times until no further improvement is observed. During testing, we use the student model to generate embedding for image retrieval. We perform evaluations on 3 popular benchmarks using both labeled and unlabeled data. Our result shows consistent improvement on 2 popular benchmarks across 3 different metrics consistently. And finally, we show qualitative results by comparing our approach against prior art. More results are available by scanning through these 2 barcodes. The conclusions here are, first, we propose a novel self-training framework to further improve the performance of deep machine learning by exploiting unlabeled data. Secondly, we propose a feature-basis learning approach to deal with the noisy pseudo labels during training. And finally, our experiment shows our approach significantly improves the performance over state-of-the-art with additionally on-label data.